Follow us. Here we are on site of the St. Lawrence River fishing for some Atlantic salmon. But while I'm fishing for these mysterious creatures of the sea, I always wonder, how much deflection can my rod take?
When companies are designing fishing rods, they can use simulation software like ANSYS to model these rods before they actually build them. This helps to save time on what it would take to get those prototypes and the money spent on those prototypes. From these software, they can model various mechanical properties such as deflection, stress, and strain. This will help them to stand apart from the competition and build higher quality fishing rods.
This image depicts the fishing rod held in place within a vice grip, seen here, at an angle that's parallel to the ground. And in this picture, it's been loaded so that it deflects. In order to make accurate measurements of the deflection as the rod bent, a white sheet of paper was placed behind the rod and a toothpick was attached to the end. The toothpick can be seen here, just barely touching the paper, and this was done so that it could easily be marked with a pen, and these markings were later transcribed into the displacement.
This is a video showing the experiment of the deflection in the fishing rod by loading marbles into a bag that was attached to the end of the fishing rod. It can be seen that marbles of about 5.4 grams in mass are loaded into a bag. 20 samples were used because we believed that this was a sufficient amount of samples to provide accurate and close results.
The experiment was conducted 3 times. The deflection in the y-axis was determined using digital calipers in a square ruler. All of these points were then plotted in Microsoft Excel.
After performing the experiment showing the deflection in the fishing rod, we were able to take the marked deflection points from the sheet of paper and plot them in Excel. 3 tests were performed to show the deflection of the fishing rod. And what this plot shows is that each test is very closely related to one another, and that our method of measuring the deflection in the fishing rod was precise and accurate. The y displacement is shown here in the y-axis, and the x displacement of the rod here is shown in the x-axis. In this plot, this is a value, the averages of all 3 tests, which were later used to show the force versus displacement graph. This plot shows the amount of deflection in the fishing rod based on a certain force applied to the tip of the rod. The force was calculated using the mass of the marbles along with the mass of the bag. As we can see here from the plot, the maximum force applied was approximately 1.3 newtons, which caused the rod to displace 450 millimeters approximately. This is particularly useful because it shows that based on an amount of force applied to the tip of the rod, how much the rod is able to deflect, which is what we are trying to model. In ANSYS,
the fiberglass was the material that was used in the fishing rod that we were physically experimenting on. As seen on this screen, this is from the Cambridge Engineering Materials selection sheet, and it represents the material properties of fiberglass. It should be noted that we were using values on the lower end of the spectrum because we believed that these represented what the fishing rod we were testing on acted on. The values used were 1,750 kilograms per meter cubed for density, a Young's modulus of 15 GPa, a shear modulus of 6 GPa, a bulk modulus of 18 GPa, and a Poisson ratio of 0.314. As well, a tensile strength of 138 MPa was used. For carbon fiber, the same properties can be seen. Similarly, the material properties for bamboo from the Cambridge Engineering Selection Pack can be seen and observed here. When we navigate back to ANSYS, these material properties can be seen inputted down here.
So here we can see the SolidWorks model, which was used in the ANSYS simulation. There are a couple important things to note about this model. Firstly is that it's made of two separate parts, the handle and the rod itself. The handle was made with the intention of using it as a rigid body because the rod that was used in our actual measurements, the handle was fixed inside a vise, so it wasn't going anywhere. Likewise, this will be modeled as a rigid body. For the rod itself, we used a constant slope from the base to the tip. That was one of the key assumptions that we made. Another was that the interior of the rod had a similar constant slope and it was hollow. So I'll go to a section view and we can see the rod. So if we zoom in here, you can see how it's hollow, and this is actually a slope as well. So the inside and the outside both slope.
The ANSYS simulation of the fishing rod can be seen here. Many steps were taken in order to get this simulation. The first step was to import the SolidWorks model into the ANSYS software. With the SolidWorks model, the handle was set to be a fixed end to represent a human holding the fishing rod while they were fishing. Next, the standard earth gravity seen here was applied to the entire rod, and as well a force was applied to the end of the rod. When we click on the force, we can see that the force applied was equal to 1.2655 newtons. This is the force that would be caused due to the weight of the bag and the 20 marbles. This was computed in ANSYS, and the directional deformation was determined to be 41.5 centimeters. The next steps were to run this simulation for each force that was determined in the experiment due to all the marbles. These values were then plotted in Excel.
After simulating the deflection of the fishing rod in ANSYS, we are able to model the ANSYS deflection results against the actual rod deflection results. The ANSYS results can be shown here as this orange line plot, and the actual rod results can be shown here as this blue line. So as you can see, there's a small offset between the data here. It can be concluded that this offset is highly likely due to the fact that we did not have access to the actual SolidWorks model of this fishing rod, possibly provided by the company. There were multiple assumptions that had to be made regarding the SolidWorks model, including the fact that the taper from the middle of the rod to the tip of the rod was uniform. However, the most important thing to note about this graph is the behavior of the rods. What these two graphs show is that when a force was applied to the tip of both the actual rod and the ANSYS simulated rod, that both rods behaved and deflected very similarly. This plot shows the different deflections of the different types of rods experienced when a force was applied to the tip of each rod. From this plot, we can observe that graphite has the least amount of deflection of all three rods. This property is particularly useful when you're fishing for heavier fish, as you can use less material to create a stronger rod with less deflection, and when a greater force is applied to the tip, it will still maintain enough deflection to keep enough tension in the line to properly fight the fish. Both rods are fairly flexible and deflect significantly more than graphite. These rods can be used to fight smaller fish, as they will bend more and keep more tension on the line. Now, for higher end fishing rods, many of these properties can be combined. A lot of the higher end fishing rods contain graphite shafts from the end of the rod around the handle to close to the tip of the rod, where the material changes to fiberglass. Now, the reasoning for this is that so the rod at the tip is very sensitive and can easily sense fish bites or any weeds that the lure gets stuck in, and you will quickly notice it as a fisherman. Whereas the graphite in the rod allows the rod to be sturdy and not deflect as much.
An interesting feature in ANSYS is shown here. This feature allows you to input force as a function of time. Companies could use this if they were creating fishing rods targeting specific types of fish. If they know how the fish reacts when they bite the hook, they could model this in ANSYS. This would show how the rod would react in real time. In this example, an increasing force as a function of time was plotted. The data points can be seen here. How the rod would deflect over time due to this force can be seen in this animation. It can be observed that the rod deflects more over time. For these values, it can be observed that the maximum deflection was 41.5 centimeters.
In conclusion, we were able to successfully and accurately model a fishing rod using geometry and material properties, able to gain a further understanding of the benefits of one material over the other in certain fishing scenarios, as well as simulate how fishing rods react to variable force similar to that which a fish would apply.